All right. Hello. So I was actually thinking, or actually there are quite a few people here, so I'm thinking actually to start with a quick show of hands before I actually get to my slides. So if anyone here has ever, and I mean like ever in their life, worked, for example, in desktop, if you could please raise your hand. No, that's okay. Embedded software? Okay, quite a few people. Much more than the desktop. Any front-end developments, for the web? I know this is C++, but maybe, okay. All right, has anyone done any package management for Linux? Oh, okay, actually more people than I expected, 2 people. Yeah, backend, anything, okay. Okay, quite a few people actually. All right, and anyone worked in anything related to DevX before? Okay, we have somebody there. Okay, so much of what we're doing in everyday life, as programmers, is being referred to as software engineering, as in engineering the software. This is, I think, like the title of 3/4 of the attendance here, according to the CppCon website. Basically, what this means, so we take some requirements, be them, waterfall, agile, user stories, or some kind of hard-written requirements, and we transform them into working code. Yeah. So as you can see, I'm going to talk about this and also how we are delivering software and how we are actually making our lives easier. So who am I? This loads, okay. So I'm a senior software engineer at Omovio, which is basically a spin-off of Continental. You probably know it as the tire company. We focus on self-driving cars. My day is actually quite diverse at Conti, so I can, for example, one day stare at USB descriptors to figure out the transfer rate, or I could be another day using some variational principles to figure out what the requirements on the accuracy of the timestamps in the system should be. But much of my work actually relates to the structure for motion part. I'm considered a geometrical computer vision expert. And for those that are not familiar with what structure for motion means, even though I think there was a talk yesterday, probably not a lot of you have attended there. So we basically look at the environment around the car. So for example, we have an object here, and as the car moves, we have a camera that's moving along with the vehicle. And based on the displacement in the images, the parallax effect, we can determine the depth of that. Yeah. Besides Omovio, I've also had a research project in planetary defense. So for those of you who don't know this term, you've seen the movie Don't Look Up. So basically, we are looking at anything that could pose a risk to humans coming in from space, usually asteroids. Yeah. This is a project that I started a long time ago. I think I've had at least 10 years since I started it. But more recently, about 3 years ago, we got a grant, which lasted until summer last year, to do this asteroid detection using a new or newish technique. New here meaning known for like 30 years, called synthetic tracking. The idea is that normally when you try to detect asteroids, you take several images, you compare them, and figure out if there is any moving object in between. But that only works if your telescope can actually see those objects. Because large telescopes cost a lot, we can't quite use those, so we want to use smaller ones. And then we'd have to take longer exposures. But in longer exposures, you can't see the object because the mirror is smaller. So what you actually want to do is to take several images and then shift them around until the asteroid falls into the same place. And then you co-add them together. Yeah, you basically add them together so that the signal-to-noise ratio increases. And doing this for every possible trajectory is called synthetic tracking. Of course, this is obviously very computationally intensive. You can see here an example of a quite fast-moving object. And this is another, this is more famous because it was actually a virtual impactor, meaning that when we discovered it, we actually had a very small probability for it to impact Earth in 2026, so next year. But after more measurements, we have excluded those possible intersection paths. So this is no worry for us. Yeah. You'll see actually my work a lot under the title Blink and You Miss It. That's because the comparison method is called blink. It used to be done by hand, so you switched between images, and that was basically called blinking. But it's actually not the fact that with blink you can't see those objects that I'm referring to. It's the fact that we can actually do synthetic tracking very fast. So when this method was discovered, it used to take like when this method was first implemented, it used to take like days on CPUs, and more recently with GPUs, you can do it in like several hours, or maybe, I don't know, 30 minutes or so. We could do it in times like, I don't know, a few minutes, 2 minutes, 5 minutes, 10 minutes, depending on how fast we want to search for the asteroids, how many trajectories we actually check. Yeah. So the common thing about the stuff that I'm doing usually is that I'm trying to first make an environment in which I can develop easily, and that makes it much more easier to actually create working software. So because I'm actually trained in mathematics, I have a BA in mathematics and a master's in theoretical physics. To me, engineering is more about tweaking and tinkering. So when I'm seeing this term engineering, I'm always thinking about, getting the code and tweaking it and, tinkering with it. And the idea is that you only have so much time you can actually work with that code. You have 8 hours a day as a programmer if you don't have overtime. So there are only so many things you can actually do there. And the question is like, what do you spend them on? And usually you would go for features. It's normal, people buy software for features. But you can also spend it on improving the runtime. Sometimes you need it to run much faster than it ran before. So you need to invest some engineering there. Maybe you need for it to run on several platforms, and you need it to be compatible with all those different platforms. Or my point here is maybe you want to invest into making your life easier. So writing the code in a way that makes it more easy for you to actually continue developing further. And also you can do the same, but for your users, which is like the ease of use of the software. This sounds a bit like, refactoring the code. So when it becomes very difficult to work with it, you just like rewrite parts of it so it's easier. But it's not just that. It's also about thinking ahead and trying to plan for how you're actually going to do it. And why this is so important for C++? Well, C++ has quite some large code bases. So if we start small, at 1 to 10 lines, you just basically don't need to care. It's just some one-liners, some small utility functions, and so on. As you go to more, you get functions, and at about 1,000 lines, you get to classes. And for these kind of examples, it's quite easy. Everybody does demos in this. When somebody shows you how to do something in a language, they're usually going to be somewhere in this area. You saw at Herbstock, they had like, 200, 300 lines of code. And this is what's usually easy to implement. Like, it's very hard to get these kind of software wrong, just because there's nothing really complex about it. Things get a bit more tricky when you're scaling up, because at some point, if you want to actually, make the software continue working, you're gonna need to have somebody take care of maintaining it. So you're already thinking about needing to have a team. So maybe for 1 to 10K lines, where you basically have some small components and libraries, you can do it with one team. But as you're scaling up, you might have to either have a much larger team, or you might think about splitting the work up in several teams. So you're already looking at a bit at organization, but this is still quite simple. if it's just a team, usually you can get a okay understanding with your teammates and things are working quite okay. But yeah, there is a lot more work there compared to simple ones. But then you go to the much higher examples. So when you're going to close in into 1 million lines of code, you're going to have several teams clearly. And one more thing that really matters here is how fast you actually change the code. So at smaller, a smaller number of lines of code, you're not going to touch that code very often. But if you're going at a larger number of code, more people working on it, and they will be working full time on that, then the change rate is going to increase. The numbers I've given here were by analyzing the Git repos of some KDE projects, and for this larger one, that's coming from a paper by Google. So as you're going into the 1 to 10 million lines, and especially 10 to 100 million lines, there are even more things happening here because at this point, you'll see a lot of projects start having their own dialect. So it's quite famous that Linux has, like the Linux kernel has its own C dialect. And when you reach the 1 billion mark, with these monorepos, you often also have the compiler into your repo and everything else. And you also get to huge teams that you need to manage. And very importantly, while the number of teams and the complexity of the code increases, you also get less time to actually test your code. So because the changes are coming in much faster, you need to spend a lot of time to actually figure out how you're going to test this in time. Like if you're having a CI pipeline, which once you reach the 10K mark of lines becomes quite important, and especially like if you're working in a team, once you reach this many teams working together on one code base, on one project, then you really need the CI to work well because it will block everybody else. But you also have the issue that everybody's pushing or at least if they don't block each other, they would be pushing quite quickly because you have so many people working in the project at the same time. So you really need to spend some effort. You need to engineer for your CI as well. So one way to actually get by and try to manage this kind of complexity is to just shift everything up. Like take some code and try to make it simpler and get more people working on several different things, or basically expand without needing to increase your maintenance burden a lot. And this is what it means, what's like keeping it simple. But the question here with how you implement this is, what do you write this for? So if you're actually writing general programming, general computer stuff, like, I don't know, desktop apps or maybe some parts of web applications, like, I don't know, web server. I don't mean like parts as in the components of the app itself, but rather these infrastructure units that need to be put together. And then the most important part is to actually get everything to interact with each other nicely. So you usually have a bunch of requirements and things you want to achieve. And the most common pattern that's being used here is this object-oriented programming. And the idea is actually quite simple because you transform your programmer into an interpreter. You get all those requirements in, and you can just translate them into business objects. And this simplifies quite a bit the, let's say, mental burden maybe of converting the requirements into code. But you also have patterns such as embedded, where actually you don't need to have all this compatibility. And what really happens is that you have a fixed set of resources and you really need to put everything into those limited resources. So what the programmers are actually doing are compiling the requirements. So you give them requirements and they need to figure out how to actually implement that. The thing about these kind of compiling requirements is that you can actually reason about the code. if you try to do this, in a regular project, you're gonna regular here meaning the usual desktop stuff. You're gonna see that you're gonna spend significantly more time on thinking about how you represent the data, and that also gives you the benefits of data-oriented design. So if you like that pattern, this actually helps. And of course, this comes with all those extra advantages of, if you think about the code, maybe you can figure out a way to make it faster and so on. But there is one more thing. You can actually spend some time thinking how to make your life easier, how to create code that's more convenient for you and your teammates to work with. And that can actually offset significantly the burden of, sitting on the requirements. So you might actually get a better product without much effort. And to get some perspective into, how do you want to do this and what are the impacts of all this stuff. First of all, one thing I've not seen a lot being discussed in these usual training resources are the costs of design patterns. Lately, I've seen, I think, like on one of the sites, can't remember exactly the name, that they've started actually giving like alternatives and when you should do one pattern or not. But usually, they're just given, okay, here is the pattern that you can use, and you can apply it. And this is what gives that kind of enterprise software that's not looked on very nicely by people working with data-oriented design. So as an example here, at some point, I thought, okay, my Astro detection software consists of several modules. Some of them doing detection, some of them doing some image processing. So maybe I can actually just put everything into one single executable, let's say, and load different parts depending on what the user wants. The idea here is that I wanted to give the user some flexibility, not just deal with whatever my code does. But you have to spend time to get the interfaces right, and you also need to set up all this inversion of control. Basically, you need to configure it every time you run the software. And this also means that when you're debugging stuff, you're not going to go directly into your code. It's going to go through whatever that container you've set up for inversion of control. So things get a lot more tricky. Remember here also, when I try to do debugging, I had to configure my IDE to start up the host application instead of the detection pipeline I was going to debug. So it adds a bit of effort, and this rolls on. There is no just one big pain point. There's like lots of small pain points, and this can actually add significant time. I think like my project got delayed by 2 months. I thought I was going to get it done in like 2 weeks or so. Just get the interfaces done and then connect everything together. That didn't quite happen. But there's also, for example, you sometimes want to think outside the box in terms of these design patterns. Again, closely related is dependency injection. So sometimes you want to switch between different ways of doing things, and you want to do this basically from outside the code that is actually doing this. So the way this is usually done, you get maybe something like a class, and you create derivatives out of that class, and you can choose one or the other. But in C++, you can also do something I call like the static dependency injection, where you take the code and you switch the implementation based on the build system. So you can actually compile one file in one configuration and compile a different file in a different configuration. And that means that you don't need to have any dynamic dispatch like you do with classes. So there is no cost with that. And depending on how you set up your ID, you can actually go to those different implementations quite okay. The thing is, if you remember the slides before with the number of lines of code, if you have a small project, it's very difficult to do this because you need a build system, to switch between files. And if you don't have more than, I don't know, 1, 2, or 3 files, then it just doesn't make a lot of sense to add a build system and test with that. It also adds a bit of difficulty with testing. Normally, the way you actually test this is by using CI and checking all possible combinations. You can also test locally, of course, like building all possibilities, but the main idea here is that you won't have in the same build all the variants. So it will not be as easy to test. But the main advantage is that you don't need to have all that extra machinery with classes. Or even if you don't want classes and you are working on it with some functions, you can get rid of that stud functional or similar stuff. Of course, this sounds like it will be useful only in embedded, because you can you basically build once, but that's not always the case. So you can build code at runtime. Basically, you can call the compiler, and this is what most of the high-performance implementations of various libraries, for example, BLAS, the basic linear algebra, are doing. In some cases, they also do pre-compiled stuff for specific hardware, but it's much more common to just configure the source with specific settings and build it at runtime, depending on what you're actually giving to it. And the idea here is that for C++, this seems very slow. The build time of C++ is usually a known issue, especially for somebody who built, for example, LLVM. You know that it can take like an hour on a usual desktop machine. Depends on how powerful your PCs are, but usually takes a lot of time. But you can also engineer for build speed. Like if you need this, if you want to do this, you can also make sure that the code that you're writing can be built quickly, and you can actually get it very quickly. So for this is not C++, to be clear. You can actually build a hello world program in 20 milliseconds. Like you can build it almost at the refresh rate of your monitor. This is the kind of speed you actually can get out of compilers. If you're trying to use a C++ compiler, that's actually a bit slower. This is still the same C code. The difference here is actually C++ links a bit more stuff, so it's actually a bit slower, but yeah, it's still quite fast. The reason why we usually have slower builds in C++ relates to stuff like the standard library and use of or abuse of templates. So how bad is this actually? Well, at some point I've built my own stud array, and to actually understand what this should look like and why I did so, let me just quickly try to show you. Let me see if I can. Why is it not showing this? Okay, it should be showing now. So this is the standard library array. So you can see this is something like 400 lines of, actually 500 lines of code. And much of it, if you look into this, is given by various macro expansions depending on the language. And you also see stuff like iterators. And if you go to the top of the file, you see a lot of headers. The thing is, these headers are actually quite pulling quite a lot of code. So if you're just, if you're trying to compile this, now you'll see around 10,000 lines of code just for STD array, which is actually a basic language feature. So arrays are usually a basic language feature. They're not, some fancy construct that we're using. This is one of the most basic data structures that we use. So with these kind of C++ plugging in the holes of C, much of the reason why std_array exists is to give it value semantics, because arrays in C have reference semantics. Well, that takes actually quite a lot of effort. So when I built my std_array, I didn't bring all that stuff in with iterators or lots of the other headers. You could see there like comparison, which actually I think is only used in the C++20 and forward. I just brought in, initializer list to be able to use the very convenient syntax where just give it the values in the constructor and it would populate the array based on that. There are also some extra goodies with rolling out your own array, in the sense that you can fix bugs. So in the C++14 language, you will actually see that there is a bug in the spec. Not sure how many people have noticed that. So when you're accessing arrays that are constant, the constant accessor is actually not const expert. It can be, because there is nothing it actually uses that's not const expert, but yeah, I guess they forgot. They saw it's not const, so they thought maybe not const expert. But the idea is that you actually get sometimes bugs in the standard library, and you can sometimes fix those by rolling your own stuff. But yeah, it's not standard, and that makes things a bit more difficult. Also, I wrote it using value initialization, so that I would be sure that all the arrays would be initialized with 0 when their constructor was called, because this is not what's happening in the normal std_array. Std_array has the same behavior as plain C, in that it doesn't initialize the data inside. But that, of course, means that the constructor is not trivial. So, yeah. That gets a bit ugly when you're using it in various places. Yeah. Okay. So, is C++ problematic for scaling software? I mean, we saw the std_array example. Well, obviously it's not very great, because it just pulls on all those extra lines just for a basic array. But it's not that bad either. You get static typing, which helps a lot in ensuring your software is correct, which can be used with templates, but that is usually an abuse of. Like if you're trying to write correct software with templates, that usually ends up in an abuse of templates, and that's like really not DevX friendly. It's going to take a lot of time to compile. It's going to have difficult error messages. That static dependency injection actually is one way to avoid this kind of template abuse. Like if you have just one specific object that you're building for, and you're using a lot in your system, you can avoid using templates for that. You can just specialize the type directly. There is also, in modern C++, if you can actually use that. In my case, in automotive, that's not something that has reached us. Maybe you remember, I think it was yesterday or 2 days ago, the talk about Misra and how they only got C++17 out now. And that was, I think, like 1 or 2 years ago. So a lot of existing automotive projects won't even benefit from that. But like if you have this modern C++, yes, you get constraints, you get concepts, you get contracts. But one thing that's a bit less clear is how much they can actually help you in making this complexity simpler. So you saw that std_array, would using constraints and concepts help with that? From what I saw, you just add some extra conditional code. Like if you, let me open the std_array a bit. So you can see that the way these headers are written, this is the GNU ISO C++ library. They're actually adding all these macros and if-defs because they're using the same header for every implementation. Yeah, sorry. zoom in a little bit? Yeah, let me try to see if I can. Okay, yeah. Yeah, so you can see that they're using all these const expr macros, which depend on the version of the language. You see a lot of if-defs with the version of the C++ and so on. So you actually get all the versions into one header. And if you're just, adding on top some extra constraints, then yeah, that's not gonna simplify things a lot. Okay, and sometimes one of the things that I feel they're not really working so well in C++ is if you're trying to use like a multi-dimensional container, either an array or some other formats, but usually it's the arrays that are most important. Or yeah, the others were usually spans. They get treated quite differently from linear arrays. To get an iterator into those, you need to somehow deal with this 2D addressing. And if you need, for example, to just copy some stuff from one side to the other, it's easier to just copy the whole thing. And if you're getting two sets of iterators, that doesn't translate so easily into a plain for loop that can be optimized into just a mem copy. Okay, so what actually is an example of scaling the software in a way that helps developers a lot? Well, I think the most obvious example is actually from assembly to C. So what you actually get there, and I think this is one of the most important advantages, is that you actually have data structures. There are some macro assemblers that help with this, but it doesn't come anywhere near what C gave developers when it came with those structs. You also get the structured programming, which I like doing it by hand in assembler is automatic for you in C. So that makes scaling software much easier. Like if you want to figure, like to see how much of a difference it is. So I saw that Microsoft has started publishing their old MS-DOS code, and a lot of utilities there are in assembly. And if you actually look at the code, you'll see the kind of effort that was made in documenting all that stuff so that the function calls, for example, wouldn't be wrong. So C helps a lot with this. A second large jump in programmer effectiveness was with automatic resource management. We got this in C++, and I think even more visible jump was with languages such as Java and C#, and that's because unlike C++, you don't even need to care about all those pointers and everything. They're just handled for you automatically. I think a lot of people here are using Python. It seems, I think that was also a point of a talk that was given this week, that many C++ programmers use Python as a second language, and the same goes there. You don't need to bother with pointers. It's a very rare thing to work with. I've seen pointers in Python, but they're like this once in a lifetime kind of thing. So this helps a lot in getting your software correct, and that helps with scaling the software. What do all these modern C++ features help in this sense? Well, let's take a look at modules. Why did C++ get modules? Well, build time. There are also other reasons here in that the way we're using headers is quite fragile. But that's also a bit of a feature, because we can, with includes, to change the code that's being sent to us. You can have multiple variants of your library, basically, being accessible by using different config options. And I'm actually going to give here two examples of how this is used. So the first one is kconfig, which is the config language of the Linux kernel, but also of the of other projects. I think here, for example, of Natex. But you also get this in C++ code. So Marlin is actually a very popular software for 3D printers. And to make it easy for their users to actually use this, you're supposed to copy these two header files for the printer that you're using. And those configure everything for you. You don't need to touch any other part of the system. You just copy those headers in, and then those control everything else that's really happening inside the code base. And that's done through a lot of macros that enable and disable stuff. Maybe some of it can actually be done with constexpr, but that I think remains to be seen. I've not seen this actually in practice. So the thing with these modules is that they actually help. They're designed to help with this build time, but they're not the same as the includes. Yeah, you don't get all that support for the config options. So what you really want is, to get the build times to be okay, and what the modules are actually supposed to do is to cache your compilation of those areas, which is memoization. We tried doing this before. Maybe some of you have seen these precompiled headers used in practice. I guess most of you completely hate them because they work very badly. Because what they really do is just take everything in your headers that you're defining for this precompilation, and they run a good portion of the compiler and then on them, and then they actually serialize the output, the internal state of the compiler, and deserialize it in the other translation units. The issue is that you never really get all the headers in all the CPP files. So you get pretty much a mix of definitions from various headers, and that's really, really bad. But the memoization is still an important point. And the funny thing is that actually Rust does this and does it with this memoization. They do it also actually because the way they're designed their compiler, they can't get any reasonable speed without doing it. Like you probably know that Rust builds very slowly. But the thing is, they actually do this so they can get those build speeds that you saw. If you don't use memoization in Rust, the compile times are just horrible. You're talking like hours and days. Yeah. So I'm gonna do a bit of detour on the safety impacts of all this DevX and C++. So a lot of the parts that help with DevX also help with safety and vice versa. For example, static typing, it will help you in figuring out what to give to as an argument to a function, but it also means that you can't get that wrong compared to, let's say, Python. It also powers quite a bit of the help you get when you're doing autocomplete, because the IDE can figure out what can't be sent to that function and can actually remove those, or can prioritize based on which types match and are in your current context. I saw this actually happen quite a bit with C++ and C#. But that's not always the case. Rust is famous for this because you get that borrow checker that in a lot of cases you run into issues with it. Because some things that are valid, sometimes you get wrong things, and like you do the wrong thing and it tells you, but sometimes you do something that is okay, but the borrow checker actually can't prove that that's right. And in that case, your experience suffers because maybe there is this construct that helps you get the job done easy and quickly and in a non-painful way. And then the borrow checker says, yeah, sorry, I can't figure that one out. And Rust is known for its safety due to memory safety. And being an embedded programmer, of course, I at some point ran into a memory corruption issue, which they took some days to actually figure out. The interesting part there is that the language in which that happened had no pointers. you could not access memory, which, for Rust, they say, we prevent raw pointer access and so on. But this language didn't even have raw. You couldn't access memory in it. Obviously, in this kind of setups, I'm talking about configuration of a hardware accelerator, which got wrong. But the point is, this language, it let you do what was essentially a buffer overflow without having any of these pointers or anything that could really go wrong in that sense. The thing is, it also didn't have any static types. It was more of a configuration language. I can actually tell you that language is Plan2ML. So I know some automotive people are actually developing some stacks based on Plan2ML now, so I pity them. But yeah, the issue with that language is that you don't get any of these checks. So even if you wanted to, if you tried to create some way of checking that's okay, you can't quite do it in that language. So the really important bit here is if you can actually add checks. There is one more thing though regarding this, which is quite interesting. The bug actually wasn't quite a bug in the sense that the value was wrong in that Plan2ML. It was actually that the hardware couldn't work with that value. So the customer, wanted a specific value in there, but you actually need to do some engineering to work with what the customer wanted and make it work on the hardware. So that's idea, of having these nice language that people could work with, even if they're not really embedded programmers, knowing C and C++ and so on. Well, sometimes that doesn't work because reality doesn't work that way. So you need to have some extra engineering to actually convert all those requirements into a working product. And there is one more nail in the coffin for Rust in terms of this safety part. If you're doing this kind of functional safety, you don't really want dynamic allocation. You will be doing static memory allocation. It doesn't have to do with pointers. It has to do with the fact that if you're doing dynamic memory allocation, if your program is not fully, and I mean completely deterministic, then you are going to have memory fragmentation. If you don't deallocate, and even in deterministic programs, if you don't deallocate correctly, if you deallocate in a wrong order, you will end up with needing to allocate a larger space than it's currently available free. And you will need to find some extra space to allocate in. And at some point you run out of memory. So all these ownership and lifetime stuff that Rust does really well for this memory safety, it doesn't really help here because everything is static. There is no ownership. These variables are static variables. They're in the BSS section, if you're familiar with linkers. Similarly, there is no, discrimination of lifetime. There is just one lifetime, the whole life of the program. You start a program and the data will be there all the time. Yeah, as I mentioned, in this kind of functional safety, you don't really get that much benefit from the Rust burrow checker. What you do get benefits from, and this is the funny part because I always keep hearing about memory safety of Rust, but there are other parts that are actually very useful for this safety. Integer promotion. So whenever you're using small integers in C and C++, they're gonna get promoted to regular sized int. And that leads to very nasty bugs. And I mean, for people that are doing functional safety, what really happens is that you get a lot of static casts. you will have lines of static casts, which is really nasty from this perspective. So yeah, if you really want to show that you're doing better in this sense, you could probably start with integer promotion. There is also another aspect which is not very well handled in many languages from my perspective. It's the memory alignment. If you have embedded systems with multiple cores of different types, like maybe one that's 64-bit, one that's 32-bit, you probably want to make sure that all your data is correctly aligned, because 64-bit integers will be accessed with an 8-byte alignment on 64-bit cores, but on 32-bit cores it depends. I know for a fact that most of the regular compilers, GCC, Clang, probably also the Microsoft one, but I've not seen it used that much in embedded, they actually, even for 32-bit cores, they use 8-byte alignment for 64-bit wins, but maybe you don't get such a common platform, and you will not get an 8-byte alignment, and then you might have some issues there. There are, of course, ways of annotating stuff, but yeah, that's some extra effort, and again, increases complexity a lot. The other nasty part of all this software development nowadays is how you actually get your software to end up in an end user's computer, including all the stuff that you need to make your software work. So one way of doing this is maybe package managers, but you have various dependencies there, and the bigger question is, how do we actually put all this stuff together? Well, sometimes you just go the monorepo way, which is you give up trying to, try to make things interact between each other. This is what the monorepo of the large software companies is. You can also try to maybe, use some ways of sending data between programs, these ones, but I think after Herb's talk, everybody knows that these are pretty bad idea. At least the ones on the left. The ones on the right, they're still quite used. Yeah. But to get your software to user's computer, you first need to make sure that you can actually bring in everything that you need. And that means that you need to have your dependencies available. So one aspect here is what package manager do you use? Because, for example, in C and C++, you also have the system package manager. And usually you get a lot of the stuff in C++ done with that. But if you're trying to build stuff for yourself, you might not have the versions that you want on that distro that you're using, or usually on Windows you don't have a distro, you just have to bring everything together. So maybe an idea is to use a language package manager that brings all those dependencies in. But the usual problem with this is that at some point, if your software is big enough, you're going to end up with a daemon dependency. Basically, you have the same software that is being depended by two of your dependencies. And things are fine if you have the same version in both cases, but what do you do when you don't? This is not very unlike how the inheritance works in C++. You can actually choose whether you want to have two versions, or if you will be using just one version for all of your dependencies. Except that you don't, because, for example, if you're looking at NuGet, what it does is it will do the same as the virtual inheritance every time. You get just one version of your software that's being used by all your dependencies. And if your dependencies don't work with that base dependency, well, tough luck. Cargo does it in the opposite way, actually. So it brings a copy of its dependency. Each packet brings a copy of its dependencies every time. which, I mean, not really the greatest thing, because you will get much more code in, and you need to worry about all those different versions. The way this has been solved in the past is actually by having a software distribution. So for anyone familiar with the Linux distros, this is what the Linux distros are. You basically just take the software and you try to make it work together. Now the thing is, this works only if you have a distro where you're actually packaged in. What happens if you don't? Well, what ends up is being a container. But the problem with containers is that, yeah, you get, again, a copy of everything inside there, and that's not a very, that's not the greatest way of doing stuff, because you basically just duplicate everything again. So this is more of a circle of bad practices. You get to choose which problems you're going to live with, actually. And this is the issue from which all this comes from, is actually how you version your software. And sometimes it's not just the versions, it's the variants. Variants here, I mean that you can build your software with different options. The profiles in Gentoo are an example. There is actually a pretty good blog post. You actually have the QR code there. I strongly recommend reading the stuff I put QR codes on, because they explain stuff a lot better than I can do. The point there is that you will have to figure out a way to version your APIs and also ABIs in a way that makes sense. One of the points in that talk is that you actually, every time you create a version, you actually have a second, you create a fork of your implementation, and you would have to keep it around. The ABI is actually not very different, but it is simpler to fix, because you can, in many cases, just rebuild everything. And if you are crazy enough, you can just do that JIT kind of thing. This is what managed languages do. And for me, for example, that's not really that much of an issue. And the problem is the API, because for that, you can't do much. Like API is generated by computers, you just rerun the compiler, but for API, you can't do that. Well, can we fix it? Normally not really, but I would say yes, under certain conditions. So, okay, I'm actually getting quite close to the 1 hour mark, so I'll be going through this a bit faster. You have reflection now in C++. This is what's the talk of, every CppCon for the past few years. Let's actually take a look at how other languages do it. I actually showed here an example from C#. I wanted to actually find something that does something similar to what Herb did, but I didn't get the time to actually update the slides with that. But what this does is actually something quite interesting. It takes documentation from the source code, and it allows you to use it in your software. And this is very, leaving aside that it's not a lot of code, but this has more to do with the library, for example. In C# you can get the change extension, which in C++ I'm not sure how easy it is to do with the stud-health system. But the more important part here is that this is just a plain C# function. You don't have extra language syntax. You can do this, all this reflection, with plain functions in the language. C++ does it with the language keywords, which I kind of consider, you add bells and whistles. Because somebody wants some feature. You could try to do it the way C# does, but I remember at some point, I can't find now the paper though, the reason why they can't do this in C++ as easily is because of API. C++ usually has this worry about breaking the API, and in case the language changes, if you are using types to represent, your types, then whenever you change the language, you'd have to change those types. So that would actually lead to potential API breakage, which is why this is not done in C++. The big problem with this is something called deformity. So this is what happens with templates, but will also happen with reflection. These are actually two separate languages. There is one language for reflection and one language for runtime. And that's extra complexity. You need to be aware of it. It basically cuts down into your runtime budget. But the thing is, with reflection, if you are treating your compiler as another piece of software, you can actually, hook into it and use it for various purposes. And you can get a lot of the benefits of what all these bells and whistles in C++ are, touted now, just by the basics of the language. In C# you can do that. There is Roslyn. So what I showed before was actually reflecting on the types, but you can also reflect on the code using the compiler. Remember modules? How I said that you want memorization? Well, in functional programming, there is this thing called functional effects, where you actually represent a piece of computation as an object. And you can actually take, let's say, the computation of a header and represent it as this functional effect. You will need some environment information because the compilers are not really pure functions, but the idea with this transformation into functional effects is that you can make it into slightly more, basically a pure function by using also the environment in which the computation is being done as an object. This is something that's called reactive programming. Probably a lot of people heard about the JavaScript React library, but the idea here is just that. You do incremental compilation. And to get these modules, basically, you just need to cache those functional effects. That's it. You just need to tell it, I want to do the caching at this point. Let's say when you're including a header. The mechanism is not really that easy to implement. There are some libraries that implement this. But the biggest advantage is, you just treat the code as data. You can use regular functions. One important thing here, remember the API, what I mentioned about the API, that that's really hard to actually make it work? Well, if you actually do this runtime reflection, you can reflect over multiple versions of the software. You can do stuff like API diff. There is a tool, a website. Unfortunately, I can't access it now. I don't know why it's blocking me. Maybe it's down lately. Called Fuget, which actually did this diff of APIs on all packages in the .NET world under NuGet. There is one more interesting thing here. Everybody knows C++ is compiled. How many people know that it's also it's also interpreted? The thing is, your C++ is working on this virtual machine. It's like this new von Neumann machine, but that's not really what happens at the hardware level. And it's when you're trying to get this on the hardware, you will see that all this nice sequential programming that you're doing, it's actually getting transformed into a set of instructions and to various execution ports on the processors. And you may think, okay, we got this freestanding. We can run C++ without an OS. Actually, you can't because you need a stack, and no CPU actually starts giving you a stack. You need to tell it where to. So you always need to run some assembly before. And very importantly, the memory that you're using is a very different. It's a different circuit, and you don't really see that, but it's basically on a bus that's not changed a lot since the 90s. And yeah, you don't have, it's also done by various manufacturers. So the interface to it is very slow, basically. An example of fast DRAM was actually an L4 cache in the Intel Broadwell CPUs, where you could actually see that DRAM is not in itself that slow. It's not really fast as SRAM, but it's not really slow in itself. But you also get the extra interface from being on a completely separate package. How bad is this? So let's consider that zeroing out value constructor, like you have a type and you want to just clean it. So let's go with ARM64. You would think, okay, it's not very efficient to just go through every element. We would just use the compiler and it would maybe give us some seamed intrinsics, and this would be quite fast. And like even if you do this through the compiler, like having multiple elements, the compiler would anyway auto-vectorize this, so it would work. Well, that's not quite what's happening. This is actually the hot loop of the memset. You'll see there is no store in this one. So most of those instructions there are just the loop. That's DC ZVA. That's actually the instruction clearing out the memory by elimination. So what does it actually mean? Well, this is data cache, and ZVA is like 0 by virtual address. The thing is, this doesn't use anything in the core itself per se. It goes directly to the data cache. You can have an ARM CPU with, like, I don't know, 128-bit seamed. This goes with 512-bit writes, because the data cache is like 64 bytes long. Any cache line is 64 bytes long. So much more efficient. And the thing is, these are not even SMT CPUs. On an SMT CPU, you'd see even bigger advantages because you could do things on the other thread, while this is just clearing data with the cache. The good part is that probably this is people optimizable, because if you see this kind of memory zeroing out pattern, you can just replace it with this. Compilers tend to do this. Okay, I guess I'm like very late. I will not discuss a lot, but I will mention this ladder of abstraction. The idea here is that what you want to do is, so far you're just like writing code, and then you're measuring the results. But you want to be able to actually work with the code, see what it does, and try to modify it. See, the real programmers, XKCD comic. Real programmers, clap their hands and the wind will actually make a cosmic ray hit the bit. The thing is, this is the same of what we're doing with optimization. Like, we're just changing some lines in the code, maybe like, I don't know, put a range broadcast in some point, and then the compiler will auto-vectorize. You don't actually tell it to vectorize. You do all these, jumbo modifications. And the idea is you want to be able to actually tell the system to do it for you. Okay, I'm gonna skip through this. This is not that relevant now. Okay, the interesting part is when we're trying to see into the future of programming languages, the most important thing is, what do you actually want to do with programming in the future? And you want to design for that. What all these new C++ things are doing, they're just more adding bells and whistles. They don't really change fundamentally the way we're doing things. As you saw with that API diff, so you could actually fix those. And even with Rust, you don't see those fixes into API, ABI, and so on. You don't get to tell it to vectorize your code directly. You still have to change the code to fix that. So the bigger question is, what do we want the programming landscape to look like in the future? And from that to actually think how we want to evolve the languages. All right, that's it. Thank you.